Hello, I'm Xiaorong Qin from China. I'm really excited to present our work, Bi-Level Meta-Learning for Few-Shot Domain Generalization. In this paper, we study the problem of few-shot domain generalization, FSDG, which is a more challenging variant of few-shot classification. FSDG requires additional generalization with larger gap from seen domains to unseen domains. We address FSDG problem by meta-learning two levels of meta-knowledge. We formulate the two levels of meta-knowledge learning problem with bi-level optimization, and further develop an optimization algorithm without higher-order derivative information to solve it. We demonstrate our method is significantly superior to the previous works by evaluating it on the widely used benchmark metadataset. Traditional few-shot classification addresses the problem of learning to classify unseen classes through knowledge of seen classes, and it is based on the IID assumption. We refer to this generalization across classes of the same domain as intradomain generalization. In real life, how to achieve further generalization when facing unseen data from unknown domains may be a problem with more practical interest. The recently attention-grabbing problem few-shot domain generalization, FSDG, is to learn a universal model via multiple training domains for good generalization to novel classes from a wide range of domains, both in and out of domains. FSDG learns novel classes across domains, and solves few-shot classification problem at an upper level involving more general domain distribution. It is interdomain generalization, which is downward compatible with intradomain generalization. Typically, the generalization ability of previous few-shot works is obtained by virtue of meta-knowledge learned through meta-learning. ProtoNet, a meta-learning metric-based method, learns an embedding space as meta-knowledge, in which instances gather around a prototype representation for each class. Such meta-knowledge is learned with the assumption that all data comes from one domain, and the generalization ability is required within the domain. ProtoNet is only better adapted to intradomain generalization of a single domain, but leads to a negative gain in interdomain generalization based on multiple known domains. For solving simultaneously in and out of domain tasks with larger and smaller generalization gaps respectively, and alleviating the negative gain and poor generalization, we proposed two levels of meta-knowledge. Those are inter- and intradomain levels, where interdomain meta-knowledge applicable to all domains is more meta-level than intradomain meta-knowledge. Specifically, we treat a base feature space as interdomain meta-knowledge, and then, we model the lower-level intradomain meta-knowledge with low-rank subspaces of the base feature space, i.e., intradomain embedding spaces, due to the variability of discriminative features across domains, as shown in the rightmost column of the figure below. For a test task from one domain, we need to find the optimal domain-specific embedding space based on the base space for classification. In addition, for fast adaptation or overfitting prevention on specific domains in the lower level, we not only learn small capacity subspace orthogonal projections as subspace representation to project base features, but also propose another interdomain meta-knowledge, namely a prior subspace. It is used for regularization shared across domains such that the lower optimization can converge rapidly to the optimal solution on each domain. We use projection metric on the Grassmann manifold in the regularization term. Naturally, we use a bi-level optimization framework for our meta-problem, where the upper layer learns the base feature space and prior subspace, and the lower layer learns a subspace for each specific domain. Given a domain distribution D, we hope to learn a base feature extractor f theta and a prior projection pc of a prior subspace so that when facing with a new domain dk sampled from D, dk-specific subspace projection pk around the prior and the domain-specific multiclass classifier hk taking in feature vectors projected can be found by the lower learning of our stochastical optimization objective. And then, we naturally use a meta-learning approach relying on the bi-level optimization framework to solve the base feature extractor and prior learning problem. In practice, we have n diverse domains drawn from D, notably, learning orthogonal projections of the subspaces directly will result in a constrained optimization problem, so for simplicity, that is done by learning a set of basis vectors WAM-rank subspace for each domain and further generating an orthogonal projection matrix P by G, W. The final empirical bi-level optimization problem called for our objective is as described. Then we introduce our meta-optimization. We use stochastic gradient descent method for our meta-problem. In the lower learning, assume that we can find its optimal parameters approximately after lower optimization for each iteration. Then we can perform SGD on metaparameters avoiding higher-order derivative information computing, and we establish the following simple lemma to explain it. You can pause the video to read it, please. The lemma lays the groundwork for our meta-optimization and shows the gradient expression of the meta-loss in our empirical objective with respect to theta and PC when using mini-batch proximal learning in the lower optimization. According to the lemma 4.1, we can develop an algorithm 1 to optimization our empirical objective without higher-order derivative information. In the meta-testing phase, we address few-shot tasks, drawn from novel classes of the seen domains or other unseen domains. About experimental results, our models set a new state of the art. Meanwhile, we do qualitative results.